Good morning, everyone. So today we'll be discussing solutions to the Laplace equations in two dimensions, wherein we will first consider a spherically symmetric charge distribution. Now, in the Laplace equation given as del squared of our potential function phi, which is equal to 0, wherein we will assume that your potential function is only dependent on the radius r and an angular component, theta, and not on the polar angle phi. Now, del squared in spherical form will be written as equation 1. Now we assume that the solution for the potential function is separable in the radial and in angular component. That is, our potential function phi would be expressed as the radial component times the angular component. Using equation 2 back to equation 1, then we can rewrite equation 1 as this. Now, dividing your equation with our potential function ZRP theta, then we get equation 3. Now, looking at equation 3, notice that the left-hand side and the right-hand side are both independent of each other. Then from that, we can set each side as a constant relative to the other, following ordinary differential equation. For the left-hand side, we can rewrite it as equation 4. For the right-hand side, we can rewrite it as equation 5. Here, n and l are both integers. The solution for the angular component p theta in equation 5 are actually Lejeune polynomials of degree n, defined within the range 0 to pi for the angle theta. Again, l is an integer. If that is the case, then when n is equal to 0, our Lejeune polynomials p0 theta is just equal to 1. If l is equal to 1, then the solution for the angular component p1 theta is cosine theta, and so on. On the other hand, the solution for the radial component zr in equation 5 has two independent roots given by r raised to n and r raised to negative n plus 1. Now, combining our results for the radial component and for the angular component, then we can rewrite our equation for the potential function as equation 6. Here, the coefficients ans and bns are just constant, which are determined by imposing the appropriate boundary condition of a given system. Now, the solution for the potential function in equation 6 is known as spherical or zonal harmonics. The problem, therefore, since we already know the form of the potential, is simply reduced to determining the constant coefficients ans and bns. And again, those are obtained by imposing the appropriate boundary conditions. Everyone, so today we will continue our discussion on solutions to the Laplace equations in two dimensions, and we'll still be talking about spherical symmetric distribution. Now, for this one, we will consider a certain exercise for which we have an uncharged conducting sphere of radius r and constant potential phi 0 that is centered at the origin. It is then exposed to uniform electric field E, which is given by a constant amplitude E naught along the z-axis. So this is the illustration of our problem. Now, the solution for the potential for the given system is given by spherical harmonics, which we have derived last meeting. This is given by the form a0 plus a1 r cosine theta plus a2 r squared, etc. So we have already derived the equations last meeting. Now, if you notice, we have considered two different solutions for the regions inside and outside the sphere because we are assuming that the two regions will be having different potentials. By applying the appropriate boundary conditions, the solutions for the potential is now reduced to determining the coefficients a's and b's. Now, for the potential inside the sphere, the potential is given by this equation, wherein we have categorically classified what would be the cause of the potential for each term. For example, A0 is the potential if you have a constant potential, which is valid for region inside the conductor. the second term, A1 R cosine theta, is the potential that is due to a uniform external field. A2 R squared P2 theta is a higher order potential that would be due to an unknown sources. B0 R raised to minus 1 is the potential due to a point charge. B1 R raised to minus 2 cosine theta is the potential due to an electric dipole. And the last term, B2 R raised to minus 3 P2 theta, and so on, correspond to higher order systems of point charges. Now, we will apply the first boundary condition for this region inside the sphere. Since we are dealing about region that is inside the conductor and it has to have a constant potential phi 0, then your coefficients an must be equal to 0 for n is greater than or equal to 1 because it has to be constant. If you notice, a1, a2, and higher order values of a's will have r dependent, which will not make it constant. Now, on the other hand, bn should also be equal to 0 for n greater than 0 or equal to 0. Again, if you notice, your functions having coefficients b's are also dependent on r, and it must not exist in our case since it has to be constant inside the conductor. Thus, we are left with just one term, and that is a0. Now, since the potential inside the conductor must be a constant potential phi 0, then we're able to get that a0 is also phi 0. And thus, this is the solution for our potential inside the sphere. Now, on the other hand, for the potential outside the conducting sphere, we have a similar form of the potential. But notice that we have categorically distinguished the coefficients having primes, just to identify their differences with the previous coefficients for regions inside the sphere. And again, our task is simply to determine the coefficients A primes and B primes. Again, notice that we have categorically classified each of the term consisting your potential. A0 prime corresponds to the potential wherein it is constant. A1 prime r cosine theta corresponds to the potential due to an external electric field. A2 prime r squared P2 theta correspond to higher order unknown sources. B0 prime r raised to minus 1 corresponds to the potential due to a point charge. B1 prime r raised to minus 2 cosine theta is the potential due to an electric dipole. And the last term, B2 prime r raised to minus 3 P2 theta and higher order terms would be corresponding higher order systems of charges. Now we will apply the boundary conditions for the region outside the conductor. Far from the sphere, that is if we take r to be having a very large number, let's say infinity, the electric field is due to the external field E naught along the z-axis. So what we will be doing now is to first apply this equation that relates electric field to the electric potential, and that is the electric field is equal to negative gradient of the potential outside the sphere. Now, evaluating by performing the derivative, we're able to get this equation here. Now, notice that if we are to set r to be a very large number, let's say approaching infinity, then our equation will diverge so that we are forced to set an's be equal to 0 for n greater than or equal to 2 so that our equation will not diverge. If that is the case, then we are just left with a1 prime and those terms having b's as the coefficient. Furthermore, we also have to set b0 prime, bn prime be equal to 0 for n is equal to or greater than 2, except when n is equal to 1, since outside the sphere, the polarized sphere appears like a dipole. It is no longer appearing like a point charge, and we do not have higher order systems of charges outside the conducting sphere. So for that, we are just left with a single term that has a1 prime as the coefficient. Now, if we are to equate this to our external field E naught k, then we will be able to get that a1 prime negative is equal to a naught. So for that, we're able to get that the potential outside the sphere would be given by negative e naught r cosine theta, and your second term would still be b1 prime r raised to minus 2 cosine theta. And later, we will just be having to solve b1 prime and to complete the equation for the potential outside the sphere. Are you ready? Alright, so good morning everyone. So today we will be discussing electrostatic images. This is another method for us to compute for the electric potential. Now, similar to the method of using Laplace's equation, wherein the equation for that is the del squared of the potential is equal to 0, the method of images also offers an alternative way to solve for the potential when the net charge of your system is 0. The method of images is one procedure that we can use to solve for the potential for a given boundary condition without solving differential equations. Remember, when we have used Laplace's equation, we are to evaluate the differential equation. Now, if you are to use electrostatic images as your method, then there is no need for you to evaluate the integral. Now, suppose the potential may be written as the potential at some distance r will be written as this. So we have phi 1r plus an integral given by this equation. Now here we have a conductor, a spherical conductor, and we are assuming that there is a surface charge density at a distance r prime from the origin. Of course, that surface integral will contribute to the potential at this distance r from the origin. And then you have to evaluate the integral over the entire surface area. The first term in our equation accounts for either a specified function of potential or an easily calculable potential that contributes at r. On the second term, again, is the integral that is contribution of the surface charge density to the potential at a distance r. The charge density may be unknown. The purpose of the images, therefore, is to evaluate what then is the value of that integral without explicitly solving the integral. We are to replace that integral with the potential phi 2r that would be due to a certain charge distribution that is usually a line or potential due to a point charge. So that is, the unknown potential will be replaced with a known potential that is due to the image charge or charges for our system. Now later, we will use this concept to solve for this problem wherein we have a point charge that is placed near an infinite conducting plane. And we want to get the potential at distance r from this plane and distance r1 from this charge. The potential will be given by two terms. One is due to the plane and the other term is due to the charge. Of course, for the charge, it is given by k, q1 and its distance, divided by its distance r1. But the question is, what would be the potential due to the plane? And we will use the method of images to solve for that later. Thank you.